Hello again. This is lecture 4 in the Introduction to Radar Systems course, and it's entitled Target Radar Cross-Section. Here we have our generic radar block diagram for the 4th time, and you can see that this lecture is going to focus on the characteristics of the targets that we're going to be detecting and how they'll affect the process of detection and tracking, all the different aspects of the radar design. Okay. Now, in the introduction, we gave a quick definition of what the radar cross-section was, and also we talked about it a little bit in the radar equation lecture, number 2. I'm going to go over and just reiterate a little bit of what I said and give a more precise definition. And as I elaborate on that, you'll understand why. Now we have the target up here. We have a radar transmitter, an antenna, and the radar is emitting an electromagnetic wave in the microwave region of the electromagnetic spectrum, and that electromagnetic wave is going out, and after some distance it interacts with the target. And you can see little arrows coming off the target. The electromagnetic radiation scatters off of all the different scattering centers and the different parts of the object. And what's really going on there is we have an electromagnetic wave interacting with a big metal object, and that interaction and the fields that follow afterwards, some of it the reflected field and the field that go on, all have to satisfy Maxwell's equations, which are the equations governing electromagnetism. And we're going to look at that in detail. But later on in the lecture, we'll get into this whole issue of the scattering mechanism. But that's big picture what's happening. Now, what we'd like to do is to characterize how that target reflects to the energy to the radar by characterizing it as an effective area. And what I said earlier, and that definition is a nice broad definition that is a good one if you have a background that's, say, in history or liberal arts or the law or political science, and you're not a scientist or an engineer. It might be a good one also for someone in the biological sciences who isn't so familiar with electromagnetism as physicists and electrical engineers would be. But if you're not used to those concepts, what it is simply it's an effective electrical area that the target sees. So we want to have and that energy is that hits that electrical, that area is scattered back to the radar. So you'd like to have an area dimension that when that wave, that plane wave from the radar hits the target, it's that amount of energy that power density hits it times an area, that's the power that goes back to the radar. Now, if you're an electrical engineer or a physicist, you can say it in a little more, rather than 10-cent words, 25-cent words. And many will, with that first definition at that level introduced, these next set of words, if I say them slowly and twice, won't become quite so complicated. And I'll go over this equation, which it is in a minute, but the radar cross-section is the area intercepting that amount of power which, if radiated in all directions uniformly, that's what isotropically means, produces the same power received at the radar. So in other words, it's the area intercepting that power that came out to the target, which, if that power, that area, radiated back isotropically, it produced the same power at the radar as the actual target does. So it's a definition. Now we want to have this definition not depend on range, And it doesn't, because we have a factor r to the fourth, which takes into account that the target will be geometrically bigger the closer it is to you. So you want to have, because what happens is the power spreads out in the sphere, and it's going to intercept a smaller area. We want to have the cross section independent of the range, and this definition of a scattering cross section, as we call it, a scattering area, is independent of range because it's basically defined in terms of a power density, and that is in mathematical terms of electrical engineers and physicists, this RCS, which is the initials, the acronym for radar cross section. We call that sigma in equations a lot. It's the limit as we go to far ranges, because we're in what's known as the far field of the radar, where the energy, the sphere is so big that it appears to be flat when it hits the radar. That flatness is we call a plane wave. It's 4 pi r squared times the electric field that's scattered by the target, divided by the electric field that's incident on the target. And with this exact definition, the scattering could go off to the sides. So the radar cross-section, you can see, is dependent on the angle that you look at the radar. And we'll look at that issue in the next view graph. And the units of the radar cross-section are an area. Okay? So I think I've gone over this definition of the radar cross-section at different levels, which I know we have an audience with many different levels of knowledge of electromagnetism, and I hope one of them settles well with you, okay, given your background. Okay. Now, what does this RCS, this radar cross-section, depend on? And I'm just going to talk about things in a general sense now, and we'll get more specific later. Well, first it's going to depend on the frequency of the electromagnetic radiation, of the electromagnetic wave, the microwave energy that's going out and bouncing off the target. Because you're going to see that that later on when we look at just a simple, if the target were a simple sphere. It's going to depend on the frequency. We brought up the concept in the introduction of polarization, the orientation of the electric field vector, and it's going to be dependent on that polarization. It's going to depend on the target's characteristics, the size of the target, whether the target's a good conductor, it's made out of metal, or it absorbs, parts of the airframe absorb electromagnetic radiation. The size, the shape, the material, as I said, and the orientation. You'd expect if you had a long cone of like a missile-shaped object, if it was pointed right at the radar, not as much area would be as intercepted as if it were traveling tangential to the radar and the radar beam was hitting the side, broadside, so to speak. And it can also depend in another way on the location of the receiver. We have two kinds of ways we can operate radars. One we call monostatically, where the transmit antenna is located at the same location as the receive antenna. Okay? And then there's what we call bistatic operation, where you have one antenna that you transmit energy out with and another antenna that you receive energy with. You can remember from the first lecture I showed you that example of that World War II radar, chain home system, that had one set of towers where the transmitting antennas were located, another set of towers where the receive antennas were located. That's a bistatic radar system. There are bistatic radar systems that exist right now. Most of them are monostatic. Now you can imagine when you have a bistatic radar system, when designing that system, you're going to want to know the bistatic cross-section. That is, the cross-section not just as a function of the orientation of the object, but the orientation of the radar relative to the object and also the orientation of the receiver. So that you're going to have to put in both of these orientations, both of these locations relative to the orientation of the target, and so therefore the bistatic cross-section data would be a lot bigger. There wouldn't be just a cross-section number when you're located here, looking nose on. There'd be a cross-section number when you're looking nose on, and different sets of angles off the side. It's another whole parameter you'd have to worry about. And then lastly, in most cases, for most radars, the radar is far away from the target, and therefore the characteristics we compare are the size of the antenna to the distance to the target. And when you're in the target is located far, far away from the antenna, we call that the far field, because the wave that hits it is effectively that plane wave that I talked about earlier. But when the target is near the radar, as it could be a missile that had a radar seeker in its nose, when that missile got up close to the target, it would be close, and it would be in what we call the near field. And the cross-section in the near field is different because the electric fields that are seen are different, because the target will see electric fields from different angles of the antenna, where they'll all appear to come from one point if it's very far away. So there's an awful lot of different factors that determine what make up the radar cross-section. Now, if you're the person who's building an aircraft, say, and you don't want someone to see you coming, you're viewed by the radar as the threat, you know. And what can you do? What can you do? Well, if you look at the radar energy that's received, this is all the factors that determine what the energy is that's received back at the radar. And the bad guys, the threat, they don't control the power of the radar. The other person does. Anything to do with the radar, like the gain of the antenna, its size, the distance to the target. Well, when you get in there, it's not under your control. The losses in the radar you don't have under control, and how long the radar dwells on the target to collect energy you don't. Size of the antenna. The only thing you have under your control is the radar cross-section, how big your target is. Obviously, you want it small if you don't want to be seen. So the question is, that's why it's very important to understand what makes up the radar cross-section. Okay? So we're going to look at what makes up that radar cross-section, and we're going to go through a whole set of 3 different sets of issues understanding the issue. First, we're going to look at what are typical levels of radar cross-section. Give you the ballpark, you know, how big is a ship? How big is an airplane? You know, that kind of thing. And what do they depend on? And now, and then when we're going to look in detail at the mechanism that when an electromagnetic field hits, the electromagnetic wave composed in the electric field and the magnetic field, you know, that microwave energy hits the target and interacts with it. What are the scattering mechanisms? And what are typical contributors to the signature? That is the backscatter. Because most targets aren't simple ones. You'll see in a minute. They're very complex. And it's going to be the addition of a whole bunch of different factors from a whole bunch of different things that contribute to generate that whole radar cross-section. And then when we understand the mechanism, we're going to say, well, gee, how can we understand what it is? What's the number that comes back? There are obviously kind of 2 things you can do. You can measure it, or you can get theoretical and develop models and predict what it is. And then you can measure it and see how well you did, and back and forth, and get good at predicting. So those are the 3 different areas we're going to go over today. Okay, next. The first thing one would want to do when one looks at how big are things is you want to look at the simplest object first. And the simplest object is a sphere. You know, you think of a sphere out there in space and a radar beam hits it. Well, you orient a metal sphere and its radius A. You know, you orient it any direction, you're going to get the same cross section because it looks the same to the radar. Okay, and now let's say, okay, we hit it with a certain wavelength. Now, if we hit it with any polarization, with the electric field going in any direction, it's going to get the same answer anyway, so it's independent of polarization too. But if we hit it with different wavelengths, we're going to see how the cross section varies if a different size of the sphere relative to the wavelength. And it behaves a lot differently in different regions. And we have three regions that basically you break things down into. Now, first of all, we're always talking in these calculations in the far field. We're far away from the radar. But we're only looking at the size of the wavelength of the radiation to the radius of the sphere. Now, when the wavelength is much greater than the size of the sphere, we're in the so-called Rayleigh region. And a British English scientist, Lord Rayleigh, did some work with electromagnetism, and not electromagnetism, but scattering. And when he did that, he realized it was the interaction of light and particles, that when you took light and you interacted it with particles, that the way things behaved is they behaved in that the size of the amount of scattering you get depended on the 1 over the 4th power of the wavelength. Very strong dependence. In other words, the cross-section got bigger and bigger and bigger to the 4th power. You say, oops, that's a linear line. Well, we've got a log scale here. And here is 1,000th, 100th, 0.1, 1, and 10. And what we're measuring is the radar cross-section normalized to pi r squared, okay, which is just the area of a circle, okay, just the area of a circle. So, and then we're comparing that on this axis to the circumference of the sphere divided by the wavelength, okay, and we see as we go down here and here and here, we're going to bigger and bigger size objects. And now here's that Rayleigh region where the wavelength is very big relative to the size of what we're looking. And down in the other end we call the optical region, and that's where the wavelength is very small relative to the object. Optical, our eyes. So our eyes are up in this optical region, and when we see an object with electromagnetic radiation called light, the cross-section that we see is just pi r squared. What we see is at pi r squared, you know, when we're way out here. Funny things are happening in here. A scientist called M-I-E, he did a lot of work looking what happens when I took an electromagnetism course. The professor wrote a skull and crossbones in this area, because that's a hard one to calculate. For complex objects particularly. This is the resonance region, and I'm going to explain why. And it's because of the mechanism. The mechanism from that sphere is actually pretty sophisticated. Okay? And what we're going to see in that resonance region is there are oscillations in the cross-section, you obviously see, and the backscattered wave that comes back from the sphere is the sum you get of all the energy is the backscatter wave from the tip of the front part of the sphere and a wave that creeps around the back of the sphere and comes back. And as it creeps around the back of the sphere and comes back, it's going to interfere constructively or destructively, depending upon, and you can see here it's adding constructively and then destructively and constructively and destructively, and then it damps out to just the optical number. Okay? And in the optical region, surface and edge scattering occur, And that's what we get. Okay? So that's you see, gee, you think a sphere would be very, very simple, but it's actually a pretty complex entity. Now what's happening with this creeping wave? If you take a very, 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 very short pulse and you send it off to a sphere, and then look at what happens to the as that electromagnetic wave interacts with the sphere. John Reinstein and a colleague were able to, and this is from a published paper that he wrote, were able to calculate what the return is from the specular, which is right off the tip of the sphere, and then that wave that creeps around the back. And for the case where the radius of the sphere is equal to the radar wavelength. And you can see this is actually the pulse shape you're looking at in each case. And the specular return is calculated, comes down right on the money as to what you'd expect it to be. So this is back, you can actually measure that creeping wave. This is an example of that. Another example which shows you that the cross-section can be very different depending on where you're looking at it. And it's an object that's relatively easy to calculate, is a cone sphere. You take a cone and then at the back of it you make it a sphere. So you take on a cone and a sphere and you look at that, and that's a trivialized model of a reentry vehicle of a missile. If you've ever gone anywhere and see what a reentry vehicle of a missile is, they make the front part of it like a cone so that it'll go through the atmosphere smoothly. There's no big deal there. But we just put on the back of it a little hemisphere. And so it's readily calculable. And here we see this blue line and this polar plot is the radar cross-section of it. Now if we look, and here's the trajectory of that reentry vehicle sort of coming in. And in the forward direction, the cross-section that you see is 1,000th of a meter square. Wow, very, 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 very small. And then as you go out an angle, and then you look at this side region here, this specular it's called, this specular region is huge. And there's a peak that's 100 meters squared when the angle is such that you're looking perpendicular at the specular region. If you're looking back at the rear aspect, you're going to see the cross-section of a cone, of a hemisphere, and at rear aspect it's 0.75 meters squared. Okay? Now here are the rings that we've marked in dashed lines are values in cross-section relative to 1 dBsm, relative to 1 meter squared, and they're marked in dBs. So this is really a log scale, and each ring of the circle is an order of magnitude greater in cross-section. Okay? So you can see that this 100 meters squared is almost 2.5 orders of magnitude more than over here, than this point in here. 1, 2. Okay? Excuse me, this part in here. So what you basically you can see is the huge difference in cross-section. Okay. Now, for some typical objects that you might think, you say, okay, how big is a helicopter? How big is a boat? How big is a man, a bicycle, a bird, an insect? And these are well known and documented in many different radar introductory texts. A simple single-engine aircraft that an air traffic control radar would like to see is about 1 meter square is its radar cross-section. A 4-passenger jet, 2 meters squared. It's got some streamlined paths to it. A jumbo jet, like a 747, 777 or something, 100 meters squared. Jet fighter, 6 meters squared. Small open boat, 0.02 meters squared. Probably a 20 to 30 foot small pleasure boat. Okay? good-sized cabin cruiser, 10 meters squared. A ship with 5,000 tons of displacement, huge, 10,000 meters squared. Truck or automobile, bicycle, a man, about 1 meter squared. Birds and insects, very, very small. But we're going to see later lectures that in your radar coverage you can have millions of these, and they can add together in flocks to give sizable cross-sections which can be seen by radars. So we'll put them down there too. But they vary all over the place, the cross-sections do.